Okay, now we have found the eigenvalues and eigenvectors for this matrix A. The next step is to get the general solution using these two eigenvalues and eigenvectors. Now, the first solution that corresponds to this eigenvalue and the corresponding eigenvector, let us say that is x1, and this is a vector, and x1 equals to e to the 2t, 2 is lambda t, and then the corresponding eigenvector which is 1, 4. The solution that corresponds to this eigenvalue and this eigenvector, which is x2, equals to e to the lambda t, but now lambda equals to -1, so you have e to the -t times the eigenvector 1, 1. Okay, so these are the two solutions that corresponds to the eigenvalues and eigenvectors. Okay, now to get the general solution, what we need to do is we need to consider a linear combination of these two. So let us say the general solution x equals to c1 x1 plus c2 x2. We have c1 times what is x1, x1 is e to the 2t, 1, 4, plus c2 times e to the -t, 1, 1. And here c1 and c2 are arbitrary constants. Okay, so this is the general solution for this particular problem. Okay, so now this is part A. So now let's go to part B. Now our goal is to find a particular solution that satisfies this initial condition. Our initial condition says when time t equals to 0, your solution vector x should be equal to 1, 0. So let's evaluate our general solution at time t equals 0. If we do that, you will get c1 e to the 2, so 2 times 0 is 0, e to the 0 is 1. So you will get c1 times the vector 1, 4 plus c2 times, again you will get e to the power 0 here, e to the power 0 is 1, then you will get the vector 1, 1. And our problem says this solution at time t equals 0 equals to 1, 0. Now, if you simplify the left hand side, you will get c1 plus c2 equals to 1, and then 4c1 plus c2 equals to 0. So now we have two equations with two unknowns, and if you solve this system, you should get c1 equals to -1/3 and c2 equals to 4/3. It is not difficult to solve this system. If you want, you could subtract equation 1 from equation 2, then you could eliminate c2, and you will get 3c1 equals to -1, therefore c1 equals to -1/3. Once we have the value of c1, using the first equation, we can calculate the value of c2, which equals to 4/3. So the solution that corresponds to this initial condition is, say, x of t equals to c1, which is -1/3. I am going to write it here. -1/3 times e to the 2t times the vector 1, 4 plus 4/3 times e to the negative t times the vector 1 1. Okay. So, now again this is a 2 by 1 vector and this is a 2 by 1 vector, and if you simplify your right hand side you will get 2 by 1 vector. The first component of that 2 by 1 vector corresponds to, let us say, x1, little x1, and then the second component corresponds to the dependent variable little x2. Okay. So, with this I finish the second example. Now, in these two examples what we did was we solved a system of differential equation where this coefficient matrix A gave us two distinct eigenvalues, real eigenvalues. Okay. So, with this I finished the first case, and next we are going to consider the second case, which involves complex eigenvalues. Thank you.